All right, let's take a look at series and parallel inductors and how we can get the equivalent circuits in the two respectively. Just a quick summary, we'll find that with inductors, the series and parallel equivalence is pretty much the same as you would with resistances. Okay, so a series circuit with inductors in series, when we simplify it to get the equivalent circuit, the equation is going to be the same as if it was resistance, and same thing with parallel. But let's go ahead and derive that. Okay, so assuming we have a circuit with a bunch of inductors in series, you got the voltages across each one of those inductors. We want to determine what our equivalent circuit would be. Okay, so what we're going to do is we're going to apply Kirchhoff's voltage law to this loop. So we're going to apply KVL to the loop. And when we do that, we see that we have voltage is equal to, our total voltage is V1 plus V2 plus V3, V3, all the way up to the number of inductors, potential inductors we have, so V sub n. Then we're going to substitute V sub k is equal to L sub k di over dt, and then we plug this into this equation up here and then just rewrite it. So then we say, well, V is going to equal to L sub 1 di over dt plus L sub 2 di over dt plus L3 di over dt, all the way up to our last inductor, L sub n di over dt. We factor out the inductance, L1 plus L2 plus L3 plus L sub n times di over dt, and then we can rewrite this as the sum from k equals to 1 all the way up to n, L sub k di over dt, and that's going to give us our equivalent inductance, di over dt. Okay, where L equivalent is equal to L1 plus L2 plus L3 plus L sub n. So this is our equivalent inductance when we have inductance in series. So here we see that inductors have same behavior as resistors. Okay. So now let's look at inductors in parallel. Okay. So scroll down a little bit. Let's take this guy up here. Okay, so now we have inductors in parallel, and we have these branches coming down with currents at each one of those branches. So we want to find the equivalent. We want to find the equivalent circuit. In this case, what we're going to do is we notice that the inductors have the same voltage across them. So inductors have same voltage across them. Okay. So we're going to use Kirchhoff's current law. So using KCL, we see that current is going to equal, I is going to equal to I1 plus I2 plus I3 all the way to I sub n. Alright, and then we can substitute. We know I sub k is equal to 1 over L sub k integration from t naught to t v dt plus I sub k t naught. So we're going to take this guy, this relationship, and just substitute it in for the above equation. And so let's go ahead and do that real quick. So we're going to say I is going to equal to 1 over L1, the integral of t naught to t v dt plus I1 t naught plus 1 over L2, integral from t naught to t v dt plus I2 t naught plus down here 1 over L sub n, integral of t naught to t v dt plus I sub n t naught. We factor out the reciprocal of the inductance, so we got 1 over L1 plus 1 over L2 until we get to our final inductor, integral t naught to t v dt plus I1 t naught plus I2 t naught all the way to I sub n t naught. Alright, and then we're going to rearrange this equation some more, simplify it some more. So I'm going to write it over here. What this is telling us is we're taking the sum from k equals 1 to n, 1 over L sub k, integral t naught to t v dt plus the sum of k equals 1 to n of I sub k t naught, which is all equal to 1 over L equivalent t naught to t v dt plus I t naught, where our L equivalent, 1 over L equivalent, is equal to 1 over L1 plus 1 over L2 plus 1 over L3 all the way to our final inductor N. And that's how we derive this relationship here. And as you see, this is the same thing that we would have if we were using capacitances. Okay, so note, so let me go and write this down. So same parallel combination, so the parallel combination resembles that of resistors. Okay. And the other thing we note is that, let me go ahead and write this up here, scroll up. The initial current IT naught through our equivalent inductance at T equals T naught is expected by KCL. By Kirchhoff's current law, to be the sum of the inductor currents at T0. So what that means is I T naught is going to equal to I1 T naught plus I2 T naught plus I3 T naught all the way to our final inductor there. All right. So that's how you would combine the inductors if they were in parallel. Now, just like we did with the capacitances and the resistance, we can simplify this. If we have n equals 2, we can say 1 over L equivalent is equal to 1 over L1 plus 1 over L2, or L equivalent is equal to L1 times L2 over L1 plus L2. Either one of those works, and that's how you combine series and parallel inductors to get the equivalent circuit. So come back down here. Series, we just add them up, and then parallel, you take the reciprocal and you add those up.